After we've collected the data in Analyst, we go to MetabolitePilot to process the data. And here you see the splash screen from MetabolitePilot. And it starts out asking you, where would you like to start today? And I'm going to start in the results workspace. And I'm going to open the 2-hour time point in the verapamil metabolism. Now the data you're going to see here has already been culled. I've removed many of the metabolites in order to leave some that show the correlation workspace to its best light. So let's look at the data though. I'm going to go to the parent. The structure shows up. We see the orange highlight showing where the parent eluted, and in this chromatogram we're showing all the metabolites. If I switch to the XIC, I can see where that one particular metabolite eluted. I also have the parent spectrum in the TOF MS, and you can see we're within 0.4 ppm here for verapamil. And I also see the product ion spectrum of the parent. And we want to look at that because we're going to look through the metabolites for common product ions. We want to see this 165, or maybe that 165 shifted by the metabolism, this 303, and maybe the 150. Let's switch to norverapamil, one of the major metabolites, and we're still in the XIC mode, and we can see that there are at least 3 metabolites in this table that have the same M/Z as norverapamil, which is this one here, M9, at 5.53 minutes. It shows up in orange, the others show up in blue. Notice too this M9, we're going to see that later. I just want you to remember that the peak ID in results tables are M numbers. So it's M for metabolite number 9. So after you've finished reviewing your data and saved it, which I've done before, so I'm just going to close this, we can correlate the results. This is PK data. So when we get into the correlation workspace, we have the option of opening or correlating results. We obviously want to correlate, and I'm going to add results. So I go find the data, and here we have the various time points from 1 hour to 24 hours. I'm going to open that data into the workspace. The last time I correlated was obviously this data. I would put in time for the x-axis and hours for the x-axis units, and then I need to actually put in the time. So 24 hours, 1, 2, 4, and 6 hours, and give it a name for the correlation results. So let's call this verapamil correlation in rats in vivo. Check to make sure it's going into the correlation file directory, and say OK. So if you can remember back to the results table, there were several metabolites there. There were at least 9. And we're going through all the various time points now and looking for whether or not those multiple metabolites are there, and then getting the areas and correlating that with time. So now the correlation's done. I'm going to sort by M/Z so I can find the parent easily. Click on that, and I get a graph in the chromatogram now where I have all the various time points overlaid. And I can zoom in on them and see how reproducible my chromatography was. Or if I don't want them all overlaid, I can look at each one individually. So there's 2 hours, 4 hours, 6 hours, and 24 hours. So very reproducible chromatography. We've also got the spectra overlaid, and you can see how reproducible those were as well. So 0.2900 to 0.2903, so we're 0.3 millidaltons apart. Or we can zoom in. Notice how many times I have to zoom on the product ion. So we go from 165.0911 to 165.0913, so 0.2 millidaltons there. Notice too that the peak IDs now, instead of being M numbers, are C numbers, so they get a new number once they're correlated. All these things are nice for reviewing reproducibility in the data, but what we're really interested in is how these things behaved over time, so we want to look at the correlation details. And to make that easier, I'll make that full screen width. So now if I click this plot box up in the table, we'll get a plot of the intensity of, or the area under the curve for verapamil at the various time points. There's nothing at time 1, which we expect for in vivo. It takes a while for the drug to get into the bloodstream and circulating. It maximizes at 2 hours and then decays away over time. So here you can see with one click we can see the metabolic stability of the parent drug. That's interesting, but even more interesting is what happens with the metabolites. So let's say we want to look at this norverapamil. If I click that, we can see that it also peaks at 2 hours and decays. And let's look at the other demethylations as well. They all do pretty much the same thing, that one stage of metabolism. Another thing I could do is sort by the MS area at 2 hours, and then plot the biggest peaks. And now I've got Softspot analysis. I know what my major metabolites are. If I click on this one, it tells me it's the parent. Click on this one, it tells me it's norverapamil. This one is demethylation on one of those side rings. This one is bis demethylation, and this one is a dealkylation, loss of one of the sides of the molecule we looked at earlier. I'm going to unzoom that, and let's add in, sort back by M over Z. I'm going to add in the bis demethylations and these oxidations. Now you see that these extra metabolites are all really rather low in intensity. I'm going to switch the graph from an absolute scale for the intensity to a percent scale. When I do that, the program looks at what's the biggest intensity for any given metabolite and scales that to 100%, and then everything else for that metabolite is scaled relative to that 100%. So now we can see that some metabolites peak at 2 hours and some metabolites peak at 4 hours. So some form a little sooner. So there's that dealkylation, norverapamil, bis demethylation, the parent. And these later ones are oxidation. That's a bis demethylation that took some bit longer to occur. That one's at 4.96. This one is 5.08 minutes. And then this one is an oxidation at 5.33 minutes. And let's get a little more interesting. Let's add in the phase 2 metabolites, the glucuronides. So we have some bis demethylations and glucuronidation, and demethylation and glucuronidation. And notice these seem to all peak at about 6 hours. And it's nice when you see that the experiment shows you what you expect from biology. You expect the parent to peak early and maybe some simple phase 1 metabolites along with it. Bis demethylations and sometimes oxidations take a little bit longer to form, and then phase 2s should come up at a later time point, because we have to form the phase 1 metabolites first before we can form the phase 2s. We can also switch the graph to a bar graph and see the relative intensities of the various metabolites. We can see that some metabolites weren't formed yet at 2 hours, but are at 4 hours. And then this one here isn't in the 4 hour, but it is in the 6 hour, and this one is already gone by the time we get to 6 hours. Another graph, which really isn't a graph but it's under graph, is this table. Note that we have 14 peaks in the upper trace in the potential metabolites table and fewer in the bottom one. Whatever we've checked under the plot checkbox shows up in the lower table. There are 3 different views in the table graph. Under occurrence, when there's an X, it wasn't found, and when there's a check mark, it was found. So all these metabolites were found at 4 hours, none of them at 1 hour, some at 2, etc. And only 3 were left at 24 hours at a detectable level. I can switch to the peak area display, and now we get the areas for all the things when they were found. Or we can switch to the peak ID. Remember those M numbers that we talked about when we were looking at the results? For norverapamil, it was M9 at 2 hours. Well, there were more metabolites at 4 hours, so that same metabolite is M13 in the 4 hour, M13 in the 6 hour. There were fewer metabolites left at 24 hours, so it's M3. If we were to go back to the results workspace and go into the appropriate results table, we would find this metabolite giving this M ID number. It's also possible to create reports. The program comes with 2 canned reports already made up for you. There's a correlation summary report and a detailed report. These reports can be edited. They are templates. So if you adjust the template, you can create your own output. And the output can be in Word, HTML, PDF, or you can just print it. So we'd give it a name. And then click Generate Report, which I'm not going to do right now because that will take a little bit of time. But I will open one for you. And we'll look at the summary report. We get a list of the results files that we're correlating. So these were the various time points. We've got the 1, 2, 4, 6, and 24-hour time points. And we have a list of the metabolites that were found. So it looks like there were 14 metabolites between all those tables. We get a graph of all the metabolites, both a linear graph and a bar graph. And we get the 3 tables. We get the occurrence table, we get the peak ID table, and we also get the area table. More details in the detailed report, but I won't go into those right now. This data that I've been showing you for verapamil will be available for you to work with on the cloud after you're done viewing this presentation. The next data set I'd like to show is cross-correlation of metabolites across species for the drug nifazodone. So in this case, the drug was incubated with human, dog, monkey, and rat microsomes. So I'm going to open that correlation. And for this data, we can see that there are ups and downs in this linear graph, but I think the bar graph is actually the best way to view this data. So now it's easy to see that the metabolite shown in the graph by this green bar here is quite high in the dog and the monkey and relatively low in the human and the rat. So if we click on this plus over here, we can get all the different metabolites that we're profiling. And I believe the green I'm interested in is this ethyl to alcohol, so I click on that, and the labels move to the peaks or the apices of those bars. So actually that one, ethyl to alcohol, is the one that's higher in the dog and the monkey and relatively lower in the human or the rat. We're also interested to see if there are any unique metabolites in human. We don't see any in this data. There's also some data here. This dioxidation has reverse behavior. It's very high in the human and the rat relative to the dog, and non-existent in the monkey. When I go back to the table, we can see this, but the graph makes it easier to see these features in the data. So again, we have different ways of viewing the data. But for this data, the bar graph makes it easiest to find what we're looking for. This data will not be available for you to work with after listening to this presentation. However, there will be a PDF presentation that you can look through the data.